I want to welcome all of you. We've been going through the Malmquist Productivity Index. We have looked at the one-factor decomposition of the Malmquist. Just let me remind you of the formula. And using the data set, we were able to estimate the Malmquist Productivity Index using 4 different efficiency scores, all of which are reciprocals of the Shepard distance function. We're able to apply this to our data set that had own period efficiency scores, another own period efficiency scores, and then cross period efficiency score, and another mixed period efficiency score. We use that to obtain the Malmquist Productivity Index, which was 0.86. And we said that that is indicative of progress. But in order to see the progress well, you got to take the reciprocal of the answer. And the reciprocal will be equal to 1.162, which means that firm C progressed by 16.2% between period 1 and 2. Now, we're able to do that for firm A, B, and C. And we got to know that even though C was inefficient in both periods, it progressed in productivity. And even though firm A was efficient in both periods, in all cases, especially, it was even efficient in the cross-period terms. The cross-period, that firm stagnated. So we're able to get to this phenomenon. So I hope that you are able to get a picture of all of this. Now, the productivity score, the 16.2% improvement in productivity that C experienced, where did it come from? There are 2 ways you can find the source of productivity. We indicated the last time that the 2 sources are efficiency change and technological change. Efficiency change is your ability to catch up to the frontier. So your control, you have control of that. It is under management control, management expertise, management knowledge, and mastery, management wisdom that is applied to the input and output, which led to the firm moving closer to the frontier, moving far away from the frontier. That is a managerial efficiency change. But sometimes there are some things that can even make the firm move closer to the frontier, which is not from management, which is outside managerial control, and this is known as technological change or innovation. Either process or product innovation, R&D, learning by doing, or even taking advantage of the technological spillovers. So an industry can do well. And just because the industry itself is doing well, the firm will also do well. So those 2 are clearly things you should know, the difference between efficiencies, not just knowing them, but understanding practically what they mean. Now, let's dig into this calculation. How do you fish out efficiency change from the technological change? I wrote technical change. It's the same as technological change. If I want to multiply the efficiency change with the technological change, you'll get back the Malmquist productivity change. These are all under constant retention scale. That is why you see C, 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 C. Now, if you are doing output orientation, the only thing that will change here is the theta. The theta will change to 5. That's all, nothing else. The theta will change to 5. Okay. And that will mean that you are using output-oriented score. And remember that output-oriented scores are usually above 1 for inefficient firms. Unlike this theta, which is below 1 for inefficient firms. So when you estimate the productivity in output orientation, the score you are going to get is going to be an automatic increase if it is greater than 1. It's going to be progress if it is greater than 1. And it's going to be decline if it is less than 1, unlike under the input orientation. Take note. So let's substitute the values. By this stage, you already have these values. Okay, let's substitute the values. These are the values for each of the information at the top. Substitute them and find the efficiency change. Remember, the efficiency change here is this value, which you have here, 0.7778, divided by the own period in year 2. And this own period in year 2 is also given by 0.8 here. So 0.7778 divided by 0.8, that should give you the efficiency change. When you check it carefully, you're going to get 0.9727. Always use 4 decimal places. And then you substitute for the technological change. What do you get? You're going to get 0.8853. Remember, all of these are below 1, and therefore they are progress under the input Malmquist productivity. And so if you want to see the progress very well, that is what I've done down here. Take the reciprocals of these values, and you will notice that you will get 1.028 and then 1.13. Who can interpret the 1.028 for me? Who can interpret the 1.028 for me? $1.028. I hope you can all unmute yourself, right? Are you able to unmute yourself?
Yes.
All right, okay.
Yes, Doc.
So who can tell me 1.028? This means that firm C has done what? Firm C. Emily, I see you there. Are you there? Michael. Miriam, you should also tell Christabel.
Yes, Doc.
Can you interpret it for them, Emily?
Okay, so the 1.028 means that the efficiency change of the firm has improved by 2.8%.
Exactly. So efficiency has improved. Not efficiency change has improved, but efficiency has improved by 2.8%. Just a little. This means that managers of MC were able to improve their managerial efficiency by 2.8%. Now, remember, guys, that this particular firm, the productivity of the firm was 16.2%. This 16.2%, 2.8% of it was coming directly from managerial acumen. And the rest of the 13% was coming from the entire industry change. So what would you say was a key driver of productivity here? Was it efficiency, progress, or it was technological improvement? What was the driver of the productivity, which we saw to be 16.2%? What was the main driver of productivity? Jones, are you here?
Yes, Doc, I'm here.
Tell me the answer then.
It's
What was the main
efficiency.
driver?
Efficiency, Doc.
Why? Why? He has muted. I was asking why. Because if you are not able to tell me why, it means you did a lottery. Who can come in? Solomon. Guys, I just want you to be ready, okay? You have to be ready. Yes, Rexford.
Look, I think we are saying that technological change is what drives technological change can drive the productivity or efficiency of all the other firms. But in this case, realize that it was just firms, it was firm C was able to improve in terms of efficiency. So we can't say it was a technological change that caused everything, because one of the firms also didn't grow. So
Right.
I think it's efficiency change.
Okay, so if you were actually continuing from the answer Jones gave, then you are wrong. Then you are wrong, because his answer was very wrong. I only asked him to justify his wrong.
Okay.
If you guys look at the values here clearly, you can see that technological change was higher than efficiency change. Technological change was 13%. Efficiency change was 2.8% for firm C. So if I were to ask you that what is driving the productivity of 16.2% we saw last time, you just look at which value is bigger. And the value that is the bigger one is the technological change, because that is 13%. So the industry helped firm C to do well. Remember that firm C was inefficient in both periods, but the industry did well. Of course, there were movers and shakers of the industry. We will know that later. Firm B was the guy that shifted the industry. And when Firm B did that, Firm C took advantage of the technological spillover. That's why the 13% is more than the 2.8%. And that is how come it was. So the main driver of productivity progress was technological progress, not the efficiency progress. It's very important you use those terminologies when you are interpreting and when you are talking about your thesis and your paper and your results. Guys, this is how you learn. These practical things I'm saying, that's what you got to say in your thesis, in your work, in your exams. Okay. So we have been able to decompose the productivity change into two sources now. What if we can even find out the more sources of the productivity? What was the key source? Because you see, this technological change, 13% that you see here, maybe something is in it. And this efficiency change, something is in it that is causing that 2.8%. Let's dig in further. Why is further digging important? Because understanding the parts helps you to understand the whole. Note that down. For those of you who are writing the thesis, you got to know this. Understanding the parts help you to understand the whole. If you want to understand the entire human biological makeup, you must have a doctor for the teeth, dentist. You must have a doctor for the heart surgeon. You must have a doctor for the eyes, eye specialist. You must have a doctor for the kidney specialist. You must have a doctor, for the pregnant person, obstetrician and gynecologist. You got to have a doctor, skin specialist. All of these, you got to have doctors for them. Then you can have a GP, the general practitioner. So from the general practitioner, that is when you begin to specialize and get deeper. Getting deeper is important because it helps you to know what is driving the ill health of the person. When an individual person is sick, understanding the cause, the right source of the problem, sometimes will require a specialist. That means you are looking at the components of the whole to understand the whole. And therefore, you will know that this person is not well, not because he has a headache, but because he has some bone problem. He's not well, not because he has some eye problem. No, that is because he has some skin problem. So you're able to know the source of the ill health of the person, the source of the sickness. The same way, if you want to know the driver or the source of the productivity, you've got to dig further. So let's dig further and go through a 3-factor decomposition instead of this 2-factor decomposition. Okay. Now, let's look at the 3 different proposed decompositions in the literature. We have already seen the efficiency change and the technological change. That's on your screen. Now let's go to Fair, Groskov, Norris, and Zahn. They decompose the productivity into 3 and not just 2. How did they do that? They looked at just, yes, Rexford, you have a question?
Yes, I was saying that I was asking that the screen wasn't showing, but it's showing now.
Okay, all right. So
the screen wasn't showing earlier, but it's now.
Okay, all right. So what Fair, Groskov, Norris, and Zahn did is that they took the efficiency change you see here. Watch it. The efficiency change that you are seeing here is under constant returns. Look at it carefully. See, subscript C indicates that it's under constant returns. What they did is that they split this efficiency change into 2. So how? They looked at pure efficiency change, and then they looked at scale efficiency change. Of course, they must have a reason for doing that. Now, that means that if you should take the pure efficiency change and multiply it by the scale efficiency change, the numerator here will cancel this one. Okay. If you check this very one here, let me try and see if I can show you. This very one here is going to cancel the denominator that you see here because they are the same. That is if you multiply the 2. And again, if you multiply the 2, the numerator there, which is under VRS, no longer CRS, will cancel the denominator here, which is under VRS. And we'll get back what you have at the top here. So why this split? They did a split because you wanted to know the contribution of scale change. What is that? The size of a company can change. And when the size of the company changes, that can affect the overall productivity of the company. I'll give you an example. Let's say that a company has got a total asset of 4 billion. And the subsequent year, the company also has a total asset. Not that the industry has changed, take note. This is not technological change. But then the size of the company, maybe not the management, but the shareholders actually have pumped a lot of capital equity or capital injection into the company. And by doing that, the size has grown from 4 billion to 10 billion. So if that happens, and it happens that the company does well, managers cannot attribute that doing well to themselves. No. Remember, efficiency change is looking at performance of managers. That is efficiency change. Efficiency change is looking at managerial performance. But in this very instance, the performance is not managerial. It is also not industrial. It's also not technological. It's still within the company, but from shareholders, outside management, but shareholders. And this has led to a higher performance, which are all contained in this efficiency change. It's all contained in there. You got to know what is driving that efficiency change to be higher. And one way you can do that is to split it and call one a pure efficiency change. That is efficiency change purely due to managers' mastery, technical mastery. And then you will now have another one, which is scale efficiency change, which is due to the scale, the plant size, the size of the company, which is as a result of shareholders injecting capital into the business. Therefore, you can now know the true source of the efficiency change is not coming from managers, but it's coming from the scale. So by splitting the two, you'll be able to know scale efficiency change and then the pure efficiency change. I hope you get it. And therefore, that is what Fair and Groskop introduced. So the pure efficiency change looks at the degree to which a particular DMU gets closer or farther away, this time not from the constant returns to scale frontier, but from the variable returns to scale frontier. Because before you can introduce scale, you got to look at both constant and variable returns. And that is what is here. Scale is always capturing constant and variable returns. So you can see that it has some V part, it has some C part. It has some V part, it has some C part. In fact, if you can remember, scale efficiency itself was defined as what? Technical efficiency divided by pure technical efficiency. Just remember that. And so technical efficiency is the one is efficiency estimated under CRS. And the pure technical efficiency is the one estimated under VRS. And so the scale is looking at that. Scale efficiency looks at that. Okay. Now remember that this, the VRS assumes that size matters. And the CRS assumes that size does not matter. So the scale efficiency now brings the two into the picture. And when we go to scale efficiency change, that one also will look at how the size is affecting the productivity over time. But look at the the technological change. Fair and Groskop did not do anything with the technological change. Look at it. It still has the C. It still has a C. It's still relative to the constant returns. It's still relative to the constant returns. It's still relative to the constant returns. So even though the efficiency change has now been made to be related to the variable returns, look at it here, the technological change was not made to be related to the variable returns under Fair, Groskop, Norris exam. So later on, there was a criticism against their model. We'll come back to that. Okay, we'll come back to how the criticism actually was made for them. For now, what we want to do is to substitute the values and find this for DMU C. And I want you to note something very important here. Note that the constant returns to scale score, okay, the score for the constant returns to scale in this very example here is the same as the score for the variable returns to scale. So it's just coincidental that the score of 0.7778 is the same under CRS, is the same under VRS. So take note of that. Keep that in mind. And it's just coincidental for this very data set. Normally in real life, it's not the same. So in all of them, they were the same because the data was just 3 DMs. It's all the same. So take note that C is the same as V. Now, when we go back here to plant this into the formula, okay, if you plant this into the formula, in order to get a 3-factor decomposition, how do we get that? How do we get that 3-factor decomposition? Just substitute each one of them into the formula and let's see. So this is it. We substitute each one into the formula. So this is a pure efficiency chain, picking the values from the formula. And then this is a scale efficiency chain. And this is a technical or technological chain. So when you divide this by that, what do you get? You get a value of 0.9259723. The scale efficiency change will give us 1. Remember, that is because the CRS scores here were the same as the VRS scores. And then the technological change was 0.885. That was the same as we had before, because these guys actually consistently use the constant retention scale. So now we have a 3-factor decomposition. Then this is the result. The results are now 3 instead of 2. And all of them will make up the productivity score we had earlier. That productivity score we had, which was, okay, in case you forgot it, the productivity score was 1.162. Again, when you multiply all of this, you should get 1.162. But we have decomposed, broken down these parts into 3 for one to understand them. Okay. Now, you need to be able to explain each one of these practically when you have estimated them. And I would normally ask you to explain them. Now let's go to another 3-factor decomposition, which was to correct the anomaly in the Fair, Groskopf, Norris, and Zahn. Remember, I told you that even though they did bring the CRS and VRS in the efficiency change, they maintained the CRS alone in the technological change. So how do we handle that? How do we handle that situation? Well, Ray and Desley came into the picture to correct that problem and indicated that once you have introduced VRS into the efficiency change, you have to introduce the VRS into the productivity and the technological change. And so he brought VRS into the picture, and I want you to take notes here. He brought VRS for the technological change, but he focused only on VRS, V alone, V alone, V alone, V alone. So the technological change is the technological change coming from the VRS frontier. It is a shift of the VRS frontier and not a shift of the CRS frontier. And of course, because it's a VRS, because you are trying to introduce variability, he maintained the pure efficiency change, just as Fair, Groskopf, Norris, and Zahn did. Okay, these papers were actually published in the American Economic Review. Remember, Fair, Groskopf, Norris, and Zahn was 94 in American Economic Review, and this was also 97, 3 years later, in American Economic Review. So they were very influential papers, you know, towards the level of productivity. They were very, very influential. Now, how do you handle the skill part? And what this guy did was very, very incredible. What they did was that they took the VRS. This time they didn't just take only VRS or only CRS, but they combined them. So they looked at VRS relative to CRS, VRS relative to CRS, VRS relative to CRS, VRS relative to CRS, to capture the scale. They didn't call it scale efficiency change. They called it scale change. Of course, that is to distinguish it from the scale efficiency change. Now, why is this scale change different from the scale efficiency change? You will come to see that later when we get to the 4-factor. But note that the scale change formula is more than the scale efficiency change formula. Let me just take you back, okay, so that I can feel the scale efficiency change formula. This is a scale efficiency change formula. Look at that. The formula is made up of just 4 things. That's it here, 4 things. Okay. 4 different efficiency scores. Now, when you go to the scale change, is made up of 8 different efficiency scores. And this is the difference. So it's capturing a lot of things. And you come to see that a lot of things. The skill change here is looking at the factor that is driving the productivity from size. From size. And that is what Ray and Desi introduced. And again, it is taking care of both the VRS and the CRS. And more importantly, what they did is that they took care of the technological change, not under constant returns, but under variable returns. Because again, if you are telling me that you're going to look at the things under variable, then you have to use variable, except skill, which captures both CRS and the VRS. So when you substitute these, again, this is not difficult because all you are doing is that you are still taking the same numbers and substituting them into this long formula, into the PEC, the pure efficiency chain, into the PTC. This time it is pure technological chain, not just technological chain. Why? Because it's measured relative to the VRS. Please note, anything relative to the VRS alone is called pure, 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 pure. That is why you have this efficiency chain to be pure, because everything is under VRS. That is why you have the technological change here to be pure, because everything is under VRS. Remember that they are all raised to the power half. All raised to the power half. But not something under the scale efficiency change for the fair Groskopf-Norris enzyme. You will notice that the fair Groskopf-Norris enzyme, the scale efficiency change is not raised to the power half. But that of the Ray and Desley is raised to the power half. So those are some of the differences that you want to take note. Okay, it has 4 different efficiency scores and then raised to the power half. When you substitute all of them, you are going to get something very, very real. Of course, the interpretation of the scale change that I spoke about is what is here. Is a geomean of a pair of scale efficiencies measured on period T technology, and the other measured relative to period T plus 1 technology. The word change, which is for quantity instead of technologies. And what they did is that they looked at the measurement relative to the VRS, and this is different from the fair Groskopf and Norris enzyme, which I said, because that one was relative to the CRS. Okay, so let's substitute them and find the Ray and Desley decomposition, the result. When you do all of this, you're going to get this result. Again, you get 3 different results, and in this case, the scale change also happens to be the same as the fair Groskopf-Norris enzyme. The pure, now, if some of the answers here are the same as the one before, it's simply because we were dealing with a simple data set where the VRS score is the same as the CRS score. But in another simple example we can do, which I've done, you will notice that that's not the case. Okay, you can have different scores because the VRS scores are not the same as CRS scores. But in this very example, they are the same. So when you convert it to, when you take the reciprocal, you'll get this. And so what would you say is the main driver of productivity? It is still pure technological change. Pure technological improvement of 13% was the key driver of the 16.2% productivity, followed by the efficiency progress of 2%, 2.8%. Scale didn't contribute anything towards productivity. Scale was stagnated. So the size of the company, in this case, company C, the size remained the same between the 2 time periods. Now, let's go to the 4-factor decomposition. It's not difficult at all because what these guys did, Wheelock and Wilson, and Simon and Wilson earlier, okay, what they did was that they brought a 4-factor decomposition. What is that? Well, take the original 2-factor decomposition, all of which were under CRS. In other words, this is what I mean. This is a Malmquist productivity index. When you split it into 2 under CRS, you have the efficiency change, and then you have the technological change. what Wheelock and Wilson did was to split the efficiency change also into two, so that you have the pure efficiency change, and then you have the scale efficiency change. Then they split the technological change also into two. Then that one, you also have pure technological change and then scale technological change. Now, this latter part is new. What Ray and Desley did, and this chart I'm drawing, you should be able to draw that in your thesis. What Ray and Desley did is that they combined this scale efficiency change and this scale technological change, and they called it the scale change. So they had three-factor decomposition. And it's just a split. They combined it. Wheelock and Wilson split it. So that makes Wheelock and Wilson own become a four-factor decomposition. And again, guys, when you now multiply through all this, you get back the original Malmquist. This is like factorizing and expanding. You can factorize all of them and you get back the original Malmquist. Or you can expand them into two factors, three factor, or four factor. So this is a two factor, it's still the same as the one before. This is a two factor technological change. It's the same as the Ray and Desley one. But this scale efficiency change is the Fair, Groskopf, Norris, and Zahn. And this scale technological change was a new addition that these guys brought, which when you multiply by the scale efficiency change, you will get back the scale change of Ray and Desley. Again, this scale technological change is quite many. It's many, just like the scale change was many. It is made up of 8 different efficiency scores. Some of them are under CRS. In fact, when you look at these things very carefully, you will notice that it's not difficult because it's the same thing you are writing. Watch this. It's the same thing you are writing for this, just that the first one is VRS, the second one is CRS. The first one is VRS, the second one for CRS. They are all the same. The first one is VRS, the second one is CRS, but they are all the same. The first is VRS, the second is VRS. So that is when you take your time, you'll be able to know the clear differences. All right, let's substitute our values into this and also find the answer for the 4 factor. And all of these are examinable. Okay, so these are the 4 efficiency scores. Let's drop it now. I remember I've told you that the scale, the VRS and the CRS are the same. If not, if they were not the same, I would have given you different scores. Okay, like these are 8 different scores. Sorry, 4 different efficiency scores. I would have given you another 4 different efficiency scores for the VRS. So that becomes 8 different efficiency scores, which you will use and substitute. But in this case, they are the same. So you're going to use the same thing in the substitution. All right. So when you substitute it, this is what you get. The scale, the pure efficiency change, pure technological change, scale efficiency change, scale technological change. This is what you get. And when you now break it down, you get these. At this stage, you can take the reciprocal so that they become clearly interpretable. You can do that. When you take the reciprocal, this one is still going to give you 1.028. This will give you 1.13. So again, you can see that the main driver of productivity will be the pure technological progress. There is another decomposition. I will not talk deeply about it. I'll just show you. Okay, it's another, 4-factor or 3-factor, 4-factor decomposition, and this is by Fair and Groskopf. They gave different names. I've written this in distance functions. Of course, if you want them in efficiency, just take the reciprocal. And they call them magnitude index, input bias, and output bias. That's how, and this is only for the pure technological change. So the scale is there. So if you're looking at this, the Malmquist will be equal to the pure efficiency change times the scale efficiency change. And then instead of the pure technological change, you have times the magnitude index times the input bias times the output bias. Okay, call it a 5-factor decomposition. And again, if you read the paper by Fair and Groskop, you'll be able to get that. But I'm not going to treat that one here. It's just on the pure technological change. Now, if you actually bring this pure technological change and you decide that you are going to include Willock and Wilson scale technological change, then that is going to give you a 6-factor decomposition as well. But you got to be careful there because it is part of the technological change that make up the scale technological change. So you got to be careful and ensure that some things are canceled before you do that. But basically, you can end at this. Okay, you can end at this, giving you a 5-factor decomposition. All right. So you're welcome to Malmquist productivity study, and that is the end of the decompositions of the quantity Malmquist work. We are now ready to run this whole thing in R. Okay. But other than that, if you have a question, please ask now. Any question you can ask.